We're very lucky today to be joined by one of our experts, Reda, who will be delivering the session. There will be an opportunity at the end of the session to ask any questions. So if you do have a question, please do put it in the box and we'll do our best to get round to answering them all at the end. If there's any we don't manage to answer, we will send answers out after the event. I do hope you enjoy this session, and what I will do now is pass you over to Reda to get started. Thanks. Over to you, Reda.
Thank you, Claire. So welcome everyone to this webinar, Introduction to Containers and Kubernetes. My name is Reda Lucy. I'm a systems developer and also a systems administrator. So I do consulting and training. I'm a Red Hat, I'm certified by Red Hat in OpenShift administration and OpenShift development. And also I'm an official Red Hat certified instructor. A little bit of background about me. So I've been using Linux for the last 20 years. And I jumped into the bandwagon of automation very, very early in my career, and most of my work has been around that in different aspects of the IT industry. So. So this course is just an excerpt of what we usually deliver in our courses at NobleProg, and of course the content has been stripped down to match the format, the 30 minutes format for the presentation, and also the 30 minutes hopefully for your questions. But you will get a sense of what it is that we present. Okay, so. Okay, fine. So the agenda comes like this. We have a very first section of the course in which we get to know a little about each other. Then we delve into the content, which is introduction to containers, then fixing the virtual machine. We'll see how containers actually help with that regard. Then we will come to demystify containers. Okay, this is a very important topic because people usually, when they deal with containers, they see it as some magic box or a black box that they do not understand. So here we will literally dissect a Linux container, see what's inside of it, and see how we can reproduce it manually. Then we will delve into the container orchestration world, so Kubernetes per se. We'll introduce Kubernetes, then we will introduce what we call the Kubernetes Resources. Of course, due to the 30-minute format, we will only introduce just a couple of them, but that should give you a solid sense of what Kubernetes is about. And then we will get a glimpse of what the cloud native world is and how big it is, so that you realize that there is much more to this containerization cloud native computing movement than just containers, raw containers and Kubernetes. And of course we'll conclude. So this is usually the questions we ask the very first minutes of each of our courses. So getting to know a little more about you, the audience. So usually we ask about the profile, where you come from. Are you a developer, an operations admin, architect, DBA, DevOps, NetOps, etc. What your main tasks are and what your exposure to the technologies at hand for the training are. And finally, we ask you about your specific expectations, and this is where we usually adapt the course to each and everyone present in the course. Now, introducing containers. So we will talk about life in the modern IT world, which is a distributed world. We'll see what containers are, why the need for containers, and then we'll see an example of implementations of containers for this course, for this webinar. Only one, that will be Docker. So in the modern IT landscape, excuse me. So we have containers, we have microservices, we have hybrid cloud, multi-cloud, multi-cloud deployments, etc. And this has created a world where applications and IT systems are distributed more than ever. So this brings in a new set of challenges to all the stakeholders in IT projects. So from the developer to the administrator, to the security operator, to the network administrator, etc. Okay, so what are containers? So containers are runtime environments in which processes will be executed. So emphasis on runtime environments and emphasis on processes that will be executed in that runtime environment. So why do we need containers? So let's take a bit of a retrospective here into how we deploy applications in production. So traditional deployment has been about usually purchasing a server hardware, installing a host operating system on it, and then deploying multiple applications because it is cheaper to do so. So multiple applications on the same operating system. Then came the virtualization, let's say, movement, in which we came to install the application not directly on the host operating system, on the physical server, but rather on what we call virtual machines that run standalone on something we call a hypervisor, so the virtual machine manager. So inside the virtual machine, you would have an operating system, you would have the binaries, the libraries, and then the same applications that you deployed on the physical server. Of course, you can have multiple VMs per physical server, and that is the point. Now, with containers, as you can see here, what we have is, again, server hardware, host operating system. Then we have, instead of the hypervisor, we have something we call the container runtime. We'll see what that is exactly. And then we have containers in lieu of virtual machines. So we'll notice here, binaries, libraries are there, the applications are there. Containers are separated into boxes like virtual machines, but containers lack an operating system. And this is one of the main differences. So first, let's compare traditional deployments versus both VMs and containers, meaning we'll see what the advantages of both VMs and containers are versus traditional deployments. So first thing we have is execution environment isolation, meaning that the virtual machine that you deploy can run independently of the physical server you have and the operating system you have. So as long as you have a hypervisor that can run a virtual machine, then you can have any version here of the operating system, any version here of the system libraries, and then you have your application. So there is this isolation, and it serves well. It helps a lot with the especially with end of life of the operating systems and the software running inside the VM. This helps a lot by the end of the life cycle. Then you have execution environment resource allocation. What do we mean by this? So execution environment resource allocation means that basically we are able to reserve resources for the VM, but also for the container. So a certain amount of CPU, a certain amount of memory that will be dedicated to one VM or one container. And total independence between hosts and the execution environment. And then we have, of course, reproducible execution environment. Now, let's compare this time VMs versus containers. So first thing, as we observed, there is no operating system, right? So no operating system means that no CPU and RAM would be consumed for running a guest OS. We're talking especially about the operating system. Additionally, there's no hypervisor, which means that additionally, there's no CPU or RAM that is consumed for virtualizing the hardware, which is what the hypervisor does. So this answers the question, why containers? Because we get the best of both worlds. So we get the speed of host deployment, and we get the isolation and reproducibility of VMs. Now, as an example, let's take a look at Docker and see here. This is a brief history of container technologies and also container-related technologies. Some things here are not at all about containers. For example, this one here and this one here. Okay, Google C groups and the Unix chroot syscall. So as you can see, some of these technologies existed for more than 40 years, 42 years to be precise. And we had similar technologies to containers before Docker, but never was there anything that looked like the container revolution. There was a container revolution, and that was because of Docker. But why did it exist? Why didn't it ever happen before, even though we had containers before? At least here. And the answer is this. That's because Docker solved the virtual machine design issues. Docker solved, or Docker fixed the VM. So when you get a VM, you want to deploy, when you get a virtual machine image and you want to deploy it, you create a VM out of it, but then you have to configure the VM, and you have to especially address the concerns or the considerations regarding what we call IPAM, so IP address management. So which IP address would it get? What gateway? How do we configure DNS, etc. Second problem is access management. So how do I connect to my VM? Which user should I use? Which password should I use? What protocol should I use? So this was another problem with the VMs. And image distribution. So how do I get an image for my for my VM, for example? Well, usually it has been manual download, and multiply this by the number of images that you have and the number of versions of images that you would get in maybe a month. And this tells you how tedious this task becomes at scale. So Docker solved these issues by simply removing them. So IP address management is deported out of the container to the container management system. So there's no more this logic inside the container image. The container image creator doesn't have to take care about any of these. And the user doesn't have either. So it's the container management systems that does that. Unified access management. So regardless of what your containers contain, sorry about the pun, you would have the same exact way through which you would access your system. And then you have here an automated system for image distribution, so which is what we call Docker Hub. So this is what caused the container revolution, the Docker revolution. Now, just to give you an idea about what we're talking about with containers. So we define the container as being the constrained process. So the process that runs in that box. Okay, so this is what we call the container. Then we have the image, which is the equivalent to the virtual machine image. So it's an archive that contains the file system of the container, a template, if you would say. Then we have the registry, the container image registry, which is basically an image repository. So a web server that hosts container images. Now, Docker is the first container management system, let's say that was, let's say, well managed, and it has a client server model. So here, there's a few details about it. But now let's get
or let's delve into containers. So especially Linux containers. So let's redefine what Linux containers are. So a Linux container is a regular Linux process running in a constrained environment. And here emphasis on constrained, of course, and also on the fact that it is a regular Linux process. So question is, how constrained are these processes? Well, we have these systems. So something we call C groups, control groups, namespaces, and SE Linux as virt module on, let's say, Fedora and RPM-based operating systems. So control groups provide resource reservation. So this is the size of the box. This is what implements the size of the box, of the container box for your container. Namespaces are what provide isolation for processes, networking, mounting file systems, etc. And then you have SE Linux, which provides isolation for the file systems. And if we ask a question, the question, where are these implemented? And the answer is in the Linux kernel. All of these are implemented in the Linux kernel. So to be precise here, everything that makes a container is not inside the container management system, Docker, Podman, runc, what gives, but instead it is in the Linux kernel itself. So let's do a little bit of anatomy. So let's run a container. So Docker run and then UBI being the image, and let's run bash. So this gives us a prompt with bash, with the shell, Linux shell. Then here we run sleep 1, 2, 3, 4, 5. So we just run this command that would wait endlessly. Then on the host operating system, we run PS and we can see that sleep is there. So the process running inside the container appears on the host system as just a regular process. You can see here that sleep is a child of bash, which is true, and this is on the host system. And if we kill this process here 24/7 on the host system, we kill it on the host system, and then we go back to the container terminal, and you will see that sleep was terminated. So we were able to kill the regular process that was running inside the container from outside, from the host operating system, as we would with any process. So let's sleep again. Sleep 67890, and we will look for that 67890. So what are the Linux namespaces? Linux namespaces, so we have C groups, IPC, network, mount, PID, user. So you have basically 7 of them. And each of them provide some isolation for a specific subsystem of what we call subsystems of the Linux kernel. So remember, we are running sleep 67890. Now let's list the namespaces. This is a Linux command, nothing to do with containers. And in here, you will see our sleep 6789 here, 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 and here. Okay. Especially notice these. This is the type of the namespace. And for sleep, sleep has a user namespace, a network namespace, a mount namespace, a UTS namespace, an IPC namespace, and a PID namespace. Now let's run Docker PS. So this basically this lists the containers that are running in on your containerization host, on your host operating system. Now let's run something inside the container. So let's get inside the container from another shell. So we run we do it like this: Docker exec and then the container ID and then bash if we want to run bash, and this gives us bash. And in here, if we run ps-fe, we will see that we can see our sleep command. Now let's do the same, but with 100% Linux commands without any Docker commands. Sudo, so we become root, and then nsenter, which is a Linux command. We target the process with PID 15838. And if we get inside the mount namespace of this process, the sleep process, and if we list /ls/, then we see this. But then if we run ls/ on the host operating system, we will see this. So something that is totally different, a different file system. And here we have entered inside the namespace of our running container. Inside the container, so we will check here the mount namespaces in action. We will create a file in the container file system. So this is from the container terminal. And then we ls/, we see it here. Now on the host, as you can see here, this is the host system, sudo nsenter, and then --mount ls, and then you can see that the file is now visible. So we got, in effect, we got inside the container root file system. Now, what about processes? Well, same thing. If you are inside the container, then you run basically the equivalent of PS, and you get all the processes. We have only 3. On the host, if we run the same thing, we have, well, hundreds of processes. Can we do the same with just nsenter? Yes. So we will this time nsenter with -p, meaning --process namespace. So we will share the namespace of this process here. We mount /proc, this is required, and then PS will show us the exact same thing. So we get this time inside the namespace inside the PID namespace of the container that was created using Docker. Now, how can we create our own container without Docker at all? Well, another Linux command, it's called unshare. Unshare creates a PID namespace, create a UTS namespace, create a cgroup namespace, create a network namespace, and then run me bash in it. Now, the moment you're here, this is this bash. It's not the other shell. This is a new shell. If you run ps-fe, as you can see, only 2 processes. If we check the network connectivity, the network devices, you can see here that I have only 1 network device. Obviously, on my host operating system, I have many more. So as you can see here, we created a container using only shell commands, only Linux commands. So this is the true nature of containers. So they are just regular processes that use specific features of the Linux kernel. So even the container runtime is actually more Linux itself than anything provided by Docker, Podman, or any of the container managers. So this concludes it for containers. Now let's talk a bit about Kubernetes. So Kubernetes is the 3rd generation container orchestration system by Google. It is highly pluggable, and this is something that has driven innovation around Kubernetes a lot. The 3rd generation of container orchestration by Google, Borg being the first one, Omega being the second, Kubernetes being the third. Borg is what runs your containers, is what runs basically Google search and Gmail. So it is still in use. Industry leaders are, well, I wouldn't say converging anymore. They have all converged already. Okay, so you have the leaders like Google, Red Hat, IBM, Microsoft, Intel, Huawei, VMware. This is now Docker. This company is now Docker, and of course Rancher and BitCanonical. So this is the life cycle of Kubernetes versions. So as you can see, very short life cycle, which means that innovation is very important, but also it means that stability is a concern. So people who want Kubernetes in production have to be very careful about this. Now, why Kubernetes? Because there were also other competitors to Kubernetes. Well, the reason is that it uses a declarative model. It solves actually many of the limitations of Docker and the other container managers. First limitation being that these container managers were limited to a single host. They didn't have proper networking spanning across multiple hosts. And of course, security was a concern with Docker, and that is a problem that is solved with Kubernetes. And we will see that Kubernetes is way more than just running containers. So declarative model, what is this about? So I'll describe this very briefly in our training sessions. We delve into this a bit more, and we show the true power of the declarative programming model. But here we just say that we use states as a unit of work for our declarative programming paradigm. Whereas with the imperative programming, so the regular programming languages, we use transitions or steps. What do we gain by going declarative? Well, lower code complexity, improved reliability. And then there's this bonus property, which is that you have for free self-healing systems. You can implement that very easily if you have a declarative model behind your system. This is the architecture of Kubernetes. So as you can see, it's a master-slave architecture. So we have here the master or the masters, and then you have here the nodes. So minions, slaves, nodes, these are terms that you will find in the literature. So just to be sure that we're talking about the same thing. So we're talking here about the managed nodes, the managed nodes from a central point, which is the Kubernetes master. So the master has what we call an API server. It has a database. It has a scheduler and a controller manager. So the scheduler chooses the right nodes for the pod, for the containers. And then the controller manager reconciles the current state with the desired state. So this is where the declarative model appears in terms of implementation. For nodes, we have two agents, basically. We have the Kubernetes node agent, which is called a kubelet. And then we have kuproxy, which is the Kubernetes network proxy. Now let's introduce two very simple Kubernetes resources. So talking about these resources, they are described through a desired state, because remember, we're using the declarative model, and this is specified in the YAML or JSON format, which are very simple text formats, human readable, and this is how you say, well, this is what I want created. The smallest unit of work in Kubernetes is called a pod. It is a generalization of the concept of containers. So it can house multiple containers, and it is atomic. You can have one container, you can have a pod that includes, for example, this pod that has 3 containers can only run on the same node. So either the 3 containers run on the same node, or they do not run at all. So you cannot have like a pod divided into or split into 2 different nodes. So there is the concept of atomicity. So a pod is a generalization of containers, and it provides a network interface, as you can see here, and it provides also storage. And it contains one or many containers, as you can see in this example. So if you access port 8080 of this pod, you will actually be redirected to port 8080 of this container. And if you connect to port 9990 of this pod, then you will be automatically redirected to port 9990 of the second container. Now, let's introduce what we call namespaces. So the concept of namespace is very similar to what you would have in software programming. So almost the same thing as, let's say, Java namespace, let's say, and also other languages, C++ and so on. So the concept of packages, modules, they all go into the same, let's say, the same direction. So what namespaces provide is a scoped view of Kubernetes objects. So let's analyze this from a very high-level perspective. So which we call this high-level design analysis, HLD. So the pod is a collection of processes, because remember, containers are processes. So a pod is a collection of processes sharing network and storage. And a namespace can include many pods. Now here we ask the question, what are pods similar to? Of course, if we were having a real training session, then I would let the participants answer. Unfortunately, we cannot do that in this modality. So I will answer myself. So pods, something that has, as you can see here, something that has processes running on it, something that has network interfaces, and also that has storage. Well, pods are similar to servers. And this is how pods were designed in Kubernetes. And now the question is, namespaces, what are they similar to then? Because if pods are similar to servers and the namespace can include many pods, what are namespaces similar to? Well, namespaces are similar to clusters. And this brings us to the true nature of Kubernetes. So Kubernetes can be seen as either a meta cluster, meaning a cluster of clusters, or it can be seen as a cluster virtualization system. A cluster virtualization system, meaning here that you have not virtualization in the sense of virtual machines, but in the sense that you can have like a virtual representation of clusters running on multiple nodes, running on multiple nodes, but still belonging to the same cluster. So this is what I mean by this. Now, to introduce the last part of it, let's show you what cloud native computing is about. Well, there is much, and I would say much more to cloud native computing than Kubernetes. So if we take a look at this one here, this is the landscape, the interactive landscape provided by the Cloud Native Computing Foundation. The Cloud Native Computing Foundation is the governing entity behind Kubernetes and behind everything regarding containers and what we call the cloud native movement or cloud native computing. So as you can see, extremely rich. Okay, each one of these is a full-fledged solution. Okay, so we're talking here about many things. So just to give you a few examples here, take a look at this. So we have, for example, Istio service mesh, a service mesh that manages microservices at scale and provides observability and so on. So this is just one element of what you can see here. So it's this one here, this small square. What else do we have? We have Project Calico, which provides Kubernetes networking and here especially scalable and secure Kubernetes networking. They put an emphasis, a lot of emphasis on the scalability of the solution, using usually for the network people, they use the spine leaf architecture. Then we have Knative, which is an implementation of function as a service, FaaS, or what we call a serverless. So here you have actually another landscape, and Knative being this one here. And another one is Kubeflow, which is a platform that provides artificial intelligence and machine learning operations automation. So another project that is around this containerization Kubernetes ecosystem, and it helps teams and companies embrace AI and machine learning, not only from a data science perspective, like from an individual perspective, which was the main limitation to them, but it allows companies to put AI and machine learning algorithms in production. Okay, this is one of the main problems with the AI, with applied AI in the corporate world. So, of course, there's much more, but we will stop here. So, to conclude, containerization is here to stay. It provides a lot of added value, a lot of solutions to problems that we had. It provides automation systems that help us scale, and God knows that even small or medium-sized companies also need to scale now. So this is not something that is only relevant to major companies like Microsoft and Oracle and so on, and Google. Okay, so even small and medium-sized companies need this level of automation. So I hope that you enjoyed this presentation, and I hope to see you soon in one of my courses, of course. So if you have any questions, I'll be happy to answer them.
Hi, Reda. Thank you for that. We do actually have a few questions that have come in, if I can just read them out to you. So the first question we have is, there are different versions of Kubernetes. Which one should I choose?
Thank you, Claire, for the question. So to answer this I mean, it's impossible to answer this without knowing the context. So usually what happens is the following. Either you run Kubernetes in production or not. So do you need to run Kubernetes in production? This is the first question that you need to ask. So if you need to run it in production, then you need support. Because if you run it in production, then most probably you have maybe service level agreements. You are not allowed to have more than X amount of downtime during a year. You may have also a need to have, let's say, support for migration, etc., which would require you to get a supported version of Kubernetes. Now we can divide between, we can distinguish between two different kinds of Kubernetes, what we call Kubernetes distribution. So basically versions of Kubernetes, all based on the same open source Kubernetes, but with a little something extra. So you have the cloud offerings. So cloud providers like the majors. So basically Google, Amazon, Microsoft, Azure, all providing their own versions of Kubernetes that is managed. So this we call here, this is info managed Kubernetes. And then you have other solutions that you can deploy yourself and manage on premise. Okay, so this includes versions like OpenShift from Red Hat. It includes also Rancher solutions from Rancher Labs. Pivotal also provides Cloud Foundry and the PKS, so Pivotal Kubernetes Service. Then you have Nutanix providing Carbon and so on. So there are a lot of solutions, but you cannot. There's not like one answer to every case. Okay, so it has to be analyzed. There has to be a study saying, okay, what do you need this for? What do you intend to run on it? How critical is this? Is the workload? Is the applications that you need to run on it, and then from there you can build an answer to this question. Okay.
Excellent, thank you. That is really useful. Okay, we have another couple of questions. Just 2 seconds. How do we scale pods?
Okay. Yeah, a good question. So let me draw it like this. So we have our pods. Let's say we have one pod here. Okay, so this is a pod.
If we want to scale it, we could, of course, run multiple or create multiple pods manually, but this is not the preferred method. So we have here, let's call pod 1. And in here, we have a higher level object that we call a replication set. Replication set. So what a replication set does is that it controls the amount of pods that need to be created. Okay, so here, let's go like this. So for example, if you create, so you would create, for example, a replication set, and you would say, I need this image run, I need this image, this container image run in the pod, and I need 3 pods. So in that case, the replication set would make sure that 3 pods have been created. Like this. Of course, these are identical pods. So it doesn't show here. So we can do that actually. So let's copy, paste. So identical pods with different names. Pod 2 and pod 3. Okay. And what would happen is the following. So if you want to scale, what you can say is Kubernetes is the following. Look, I created a replica set that says I need 3. Well, now I need 7. So you would modify the YAML code for this object, and then automatically Kubernetes would reconcile the actual state, so 3 pods, to the desired state, which is 5 pods, and then it would create additionally 2 other pods. So this one here and this one. There are even more advanced, let's say, techniques and objects provided by Kubernetes. So, for example, we have what we call the deployment on top of the replication set. So we have what we call Kubernetes deployments. So deployment. And basically, when you create a deployment, what would happen is that the deployment would be, after you create a deployment on Kubernetes, then the piece of code running inside Kubernetes that's in charge of observing and reconciling the state of deployments would say, oh, I have a new deployment, so I will create a replication set. And then a replication set object would be created automatically by Kubernetes. The replication set being automatically created, then the replication set would come in and say, oh, I need pods, and then it would create the pods. Okay, so this is usually the way you would work. Now, on top of this, you can have something that we call the horizontal pod autoscaler, or HPA, which would automatically adjust the number of replicas, the number of pods, for example, depending on the CPU usage. Usually that would be on the CPU usage. So if CPU usage reaches, for example, 70 or 80%, then Kubernetes will automatically by itself create new pods to match that new load that is occurring in real time. So this is more or less how you do that. There are other objects like a vertical pod autoscaler, which would do other things and so on. So as I said, this is a very, very large domain, and it is also constantly evolving. But bottom line is, this is how you would scale an application.
Fabulous. That is great. Thank you, Reda. I think we've got time for one more question before we finish. How does an application get exposed outside of the cluster?
Yeah, okay. So there is an object that you create, which is called a service. So service. This is a Kubernetes object. And what the service does is that it provides a virtual IP that serves these pods. From here, so that when you have an incoming connection, this connection to the service would automatically redirect the TCP, usually it's TCP communication, to one of the pods, and this is transparent to the user, to the client connecting to the service. They see only one IP and one domain name. There is an internal DNS server inside Kubernetes, and they see one domain, let's say fully qualified domain name. They connect to that and they get into one of the pods. If a pod were to disappear, for example, let's do this color here. If this were to disappear, then automatically the service controller, so the piece of code managing these, would sever this backend here, the link here. So the service would never expose pod number here. This would be pod number 4. Okay. From the outside of Kubernetes, there's this. So usually accessing a service is done from inside Kubernetes, so from another pod, the client pod. But from the, let's say, really the outside world, you have an additional system which is called, so here in black, which is called an ingress. So with the ingress, you basically we have the same thing, except that this time access comes from outside of the Kubernetes cluster. So all of this is inside the cluster. So run it inside the cluster. The ingress itself is running inside or the ingress controller is running inside the cluster itself, but the communication path would come from outside. So it would come like this, and then from here you would have another link coming here and then exposing each of these. Now, you may ask why I used green as a color and red for the other, and both the data flow here from the service and from the ingress both use green. This actually is by design. So let me just finish this. The red line and the green line, they have actually names. So we call the red line, we call it actually part of what we call the control plane. So all of what's in red is part of the control plane. And all of what is green is part of what we call the data plane. This is one of the design principles behind Kubernetes, and it's actually a best practice in the network world, in the networking world. So basically all network vendors, when they create routers, firewalls, switches, etc., they always separate what we call the data plane from the control plane. Reason is that if the control plane were to crash, the data plane will continue. So you will basically lose, you will be in a degraded mode. You will not be able to modify the data flow but the data flow as it was before the control plane crash will continue to work. And this is one of the design principles shown here. So this is basically how you service or how you expose your workloads, your pods and containers running inside of Kubernetes cluster.
Brilliant. Thank you, Reda. That's great. We've had lots of people asking about the recording. Assuming you registered through Eventbrite and we have your email address, then you will get a copy of the recording. If you didn't, I've just put my email address in the chat. So if you'd like to email me to request a copy of the recording, we'll make sure that gets sent out to everybody. And we'll also be putting it on our LinkedIn page. Thank you, Reda. That was a really useful presentation, and thank you for taking the time to answer the questions. I hope everybody found it interesting and useful. And if you'd like to learn any more, please get in touch with us for more information about our courses. Yeah, I think that's, unless anyone's got any further questions, I think that's everything. Thank you, Reda. Really appreciate that.
Thank you, Claire, and thanks everyone, and stay safe.
Yeah, thank you very much. Goodbye.
Goodbye.
Bye.